Welcome to part 5 of our Fourier series journey. We've spent a lot of time in the time domain, adding waves together. Now it's time to flip our perspective completely. Think of the frequency spectrum like a graphic equalizer on a stereo. An equalizer doesn't show you the audio wave itself. Instead, it shows you how much bass, mid, and treble is present. This is the core idea of the frequency domain. Instead of plotting a signal's amplitude against time, we plot the amplitude of each harmonic against its frequency. Let's look at our square wave. The fundamental frequency, key = 1, has an amplitude of 1.27. The third harmonic is 0.42, and the fifth is 0.25. These values form our spectrum. A complete spectrum actually has two parts: the amplitude spectrum, showing the size of each harmonic, and the phase spectrum, showing the starting shift of each wave. Together, they hold all the information. Notice how the amplitudes shrink as we move to higher frequencies. For a square wave, they drop off following a 1/over curve. This rapid decay tells us that lower frequencies carry most of the energy. This reveals a beautiful duality in mathematics. The time domain and the frequency domain are just two sides of the exact same coin. Neither is more real than the other. Every unique signal has a unique frequency spectrum. You can think of this spectrum as the signal's mathematical fingerprint. By looking at the spikes, you can instantly identify the fundamental building blocks. Because of this perfect duality, we can move back and forth without losing anything. If you have the spectrum, you can perfectly reconstruct the original time domain signal by summing those exact sine waves. So remember, the frequency spectrum is simply the signal's fingerprint. It's the exact same data, just viewed from a completely different, and often much more illuminating, perspective.